All right, welcome back to Rapid Office Hours. Today we're doing another Wronskian computation, but this time for complex roots. So I'm thinking in the background, I'm thinking of a constant coefficient, second order, linear, homogeneous ODE, whose roots are complex, okay? So how do I actually do this? Well, remember it's the Wronskian of y1 and y2. If that is a not identically equal to 0 function, then I know that y1 and y2 are linearly independent. So let's get started. So the Wronskian is going to be w of y1 and y2 of t. Okay, so that's going to be the determinant of y1 and then y1 prime, y2 prime. But that kind of poses an issue because the derivatives of y1 and y2 are complete nightmares. So let's go and compute that off on the side and see what happens. All right, so what is y1 prime in this case? Well, that's going to be a product rule. So it's going to be the first term, so that's e to the alpha t, times the derivative of the second. Well, chain rule tells me that's a minus beta sine of beta t, okay, plus the second term, that's cosine of beta t, times the derivative of the first term, which is alpha e to the alpha t. Okay, so that's y1 prime. So giddy up, the determinant's going to be fun. It's going to be a disaster. That's okay. Y2 prime, same thing, so what do I have? I have e to the alpha t times, let's see, this is beta cosine of beta t, good, plus the second term, sine of beta t, times the derivative of the first, which is again an alpha e to the alpha t. All right, fantastic. Well, here we go. This is going to be the determinant of what? Okay, y1 is this guy, so it's e to the alpha t times cosine of beta t. And y2, okay, let's write y1 prime because it's pretty big, but let's try and combine some terms. So what if I have a minus sign here. What if I just wrote the positive one first? So what if I wrote this as alpha e to the alpha t times cosine of beta t minus, let's do beta e to the alpha t times sine of beta t, okay? So that's y1 and y2 prime, or y1 and y1 prime. Now y2 is this guy, so that's e to the alpha t sine of beta t, and y2 prime is given by this thing. So let's write this as, let's do beta e to the alpha t cosine of beta t plus alpha e to the alpha t sine of beta t. All right, now if you're anything like me, I'm already lost in the woods and I'm like, I have no idea what I'm doing anymore. So I'm going to step back for 2 seconds. I'm going to say, okay, what am I trying to do? I'm trying to compute the Wronskian of y1 and y2. That by definition is the determinant of y1, y2, y1 prime, y2 prime. Great. I then went off the side, computed y1 prime, y2 prime. I now plug that into the determinant and now I'm going to compute the determinant. All right, fantastic. So what am I going to get? Well, it's going to be this term multiplied by this term. Okay, so if I'm just distributing the e to the alpha cosine beta t in there, what am I going to have? I'm going to have a beta. Okay, so there's the beta there. E to the alpha t will be e to the 2 alpha t. Okay, and then cosine beta is cosine squared beta t. All right, so that was this term times that term. I need to add e to the alpha t cosine beta t times this guy. So that's going to be what? Alpha e to the 2 alpha t. That's my alpha e to the alpha t. And now I'm going to get mixed terms, cosine sine. So I'm going to get cosine of beta t, sine of beta t. All right, so that was simply just doing this term times that term. That was all I was doing. So I'm going to take that whole thing. Let me put them in brackets, okay? There's always a question people ask me, they're like, why did you choose to use brackets versus parentheses? And I don't know why that's a thing. Like brackets versus parentheses, like at the end of the day, it doesn't matter. All I'm trying to do is say, look, this is something that is in this bin, whether I put curved parentheses or I put brackets, algebraically, it doesn't really mean anything, okay? So I don't care what you use, parentheses, brackets, doesn't matter, whatever you're more comfortable with, okay? So now I need to subtract the cross of these two terms, the product of those two. All right, so what's that going to give me? E to the alpha t sine beta t times this. So I'm going to get an alpha, okay, that's my alpha, e to the 2 alpha 2 alpha t, and then mixed, so cosine sine, so cosine beta t sine beta t. All right, and then I'm going to get minus beta, we'll see if we can get this in here, e to the 2 alpha t times sine sine, so that's sine squared. All right, well, luckily we were able to fit it on the board, so that's good. And now you step back and you're like, oh, great, it's a trig simplification, which means I'm going to fail. Because there's a million trig identities and all that stuff that no one remembers. So let's see. What do I have? Well, I see an alpha e to the 2 alpha t cosine sine minus alpha e to the 2 alpha cosine sine. So this term wipes out that term. So that's a miracle. And now I'm left with what? I'm left with a beta e to the 2 alpha minus beta e to the 2 alpha. So I'm going to get a beta e to the 2 alpha t times what? Cosine squared of beta t coming from this term minus, so plus sine squared of beta t. And thankfully the Pythagorean identity tells me that cosine squared of theta plus sine squared of theta is 1. So this whole thing is just beta e to the 2 alpha t. And that function is never equal to 0. Moreover, it's not even the identically equal to 0 function. Therefore, the Wronskian is non-zero and y1 and y2 are linearly independent. So we should say, therefore, y1 and y2 are linearly independent. Okay, just to be precise, to verify that we've actually concluded what we wanted to conclude. So that was a lot of algebra, a little trigonometry, and a lot of patience, but we got to show that using the Wronskian, y1 and y2 are linearly independent. Okay, so I hope that helps you on your journey of ordinary differential equations and deciding when functions are linearly independent, specifically when these are coming from solutions to the characteristic equation with complex conjugate roots. All right, so as always, like, subscribe. We'll keep this thing going. Comment down below. Ask questions. These are, after all, my office hours.